I can't hear you, sir.
Hello, can you hear me now? Hello, can you hear me now?
I can hear you now, sir.
Okay, good, fine. So let me recast what I've discussed so far. So I was trying to say that today our objective is to discuss the concept of magnetism. And in the process, we shall be looking at some properties of magnetic materials, which has to do with magnetization, diamagnetism, paramagnetism, and ferromagnetism, and also antiferromagnetism. So, but before we go deep into this concept, I would like to just give a kind of a brief introduction to what we are familiar with in our days at a young age. We all know what is called magnet. In magnet, there are two concepts called poles. We have the North Pole and the South Pole. So these are the two things that describe the properties of a magnet. So if you now have two different of bar magnets, if you bring them together and they attract each other, what tells us is that the polarity between the two magnets are of opposite sign. One is north, the other is south. But when you bring them close to each other and they are not attracting, instead of attracting, you are feeling a kind of a force in between them that is pushing your hand away from each other. This tells you that the two magnet or the two bar magnet has the same polarity, and it could be north pole or the south pole. And in between them, the force that is trying to repel them is due to what we call repulsion. It's a repulsive force. So these are things that we are familiar with in our days when we are young, but we don't really understand the physics of what is going on. So what we're trying to tell us that when you have two different poles, they will attract each other. But when you have opposite, if you have the same pole, they will repel each other. Is that okay? So now, the concept of this attracting each other through this process is what we refer to as magnetization in magnetic theory in physics. So now, when you have a material and they try to attract each other, something happens. There is something we call magnetic field that induces that attraction between the two magnets. So we need to probe further to really understand what might have constituted that property or that concept of interaction that leads to attracting each other. So, like we discussed in the case of dielectric, when you bring a material into an electric field, you have what we call electric polarization because it will induce a field. The same thing here happens in magnet. When you bring a magnetic material into a magnetic field, it will induce what we know as magnetic polarization. And this magnetic polarization depends on the properties of individual atoms or molecules that constitute the magnets. And that is what leads to what we call the interaction between them. Now, majorly what leads to this is what we know as orbital motion of electrons in atoms, because we know that electrons move or vibrate. So this orbital motion of electrons of atoms or molecules do create what we call current. And this current give rise to what we know as magnetic dipoles. When we discuss dielectric, we talk about electric dipole. So in the case of magnetism now, we discuss what we call magnetic dipole. So in many materials, the small electric current associated with the orbital motion and spin of electron average to zero. The layman explanation for that statement is that there are two polarity there, negative and positive. So once the negative and the positive crosses each other, you have a zero polarity. That is the layman interpretation of that statement, that in many material, the small electric current associated with the orbital motion and the spin of the electron average to what? Zero. So now when such atoms, when they are placed inside magnetic field, just little electron currents are generated. And by induction in the clouds of electron, the direction of which such that the magnetic field associated with them opposes the inducive field B. This capital B bold that you are seeing is what we call magnetic field. So these are known as diamagnetic substance. So what's happening here is that it is easy for us to create or to produce a material that has diamagnetic properties by bringing a magnetic material into a field, and if that happens, you will generate what we call diamagnetic material. So you cannot get a diamagnetic material without bringing them close to electric field or close to magnetic field. And once you take away the magnetic field, the materials loses the properties of diamagnetism. So when they ask you to discuss a diamagnet materials, the idea is that for you to get a material that have a diamagnetic properties, you must bring them close to magnetic field. And once they are inside magnetic field, they will produce a small current. And once you take them away from the magnetic field, they lose the current and they lose the diamagnetic properties completely. Now, there are other materials in which the atoms do have intrinsic magnetic moment on account of the fact that the current from the orbital motion and the spin of the electron do not average to zero. So in this case now, when you now have these two concepts, the orbital motion of electrons and the spins of the electron, these are the two properties that describe the concept of magnetism. So when you have both of them and the average of these two is not equal to zero, you have other materials that are being generated which are known as magnetic material as well. So but they belong to a particular class under magnetic properties and magnetic behavior. So in this case now, so both the spins of the electrons and the orbitals of electron contribute to the interactions that took place or that will take place in the process of interaction between these type of materials. An example is when such a material are placed in a magnetic field, the magnetic moment of the atom and the induced magnetism enhances the external field. This effect is more pronounced at low temperature, and we generate a material called paramagnetic substance. So at low temperature, it is easy for us to generate paramagnetic substances or materials, provided these two materials are bring together and the process, the spins of the electrons and the motion of the electrons does not average to zero. Is that taken? So every atom or molecule may be regarded as a tiny magnetic dipole with the magnetic moment with this equation 2.1. So where Qm is the magnetic pole strength, L is the pole separation, and I is the current, and the S is the area of the loop. So the effect of atomic magnet is described by the quantity called magnetization, M. So which is defined as the magnetic dipole moment per unit volume. Please take note of this definition. This, somebody can ask you to define magnetization. So it is just the magnetic dipole moment per unit volume, but it has relationship with another properties which is called susceptibility. So when you relate these two things together with magnetic field intensity, you can construct an expression or equation which is stated in equation 2.1, and this gives us M is equals to psi H. Psi here is known as susceptibility of the material, that is magnetic susceptibility of the material. So, and it's a function of temperature. It depends on temperature. The higher the temperature, the higher the susceptibility, and the lower the temperature, the lower the susceptibility of the material. So another example or another concept is what we call diamagnetism. Substances with a negative magnetic susceptibility are called diamagnetic. So what I'm trying to say is that when you compute, if you use equation 2.2 to derive susceptibility and your results turn out to be a negative result, what comes to mind is that that material that has the property that you use to compute that susceptibility is a diamagnet because it has a negative susceptibility. So diamagnetism to a greater or lesser degree is a property of all materials and will always make a weak contribution to the material response to magnetic field. However, for material that shows some other form of magnetism, such as ferromagnetism and paramagnetism, the diamagnetic contribution becomes negligible. I will discuss the concept of ferromagnetism in a few minutes time now. So substances that mostly display diamagnet behavior are termed diamagnetic materials or diamagnets. So materials that are said to be diamagnet are those that are usually considered by non-physicists to be non-magnetic. Did you get that concept? Those that doesn't belong to our own community, they will say, it is non-magnet. But we give it another name. The name that we gave to them is diamagnet. But in their own community, they call it non-magnet. If they say it in the presence of a physicist, we just laugh that, well, that is their own idea. But we know them as a diamagnet material. So, and include an example is water, wood, and most organic compounds such as petroleum, some plastic, and many metals, including copper, particularly the heavy ones with many core electrons, such as mercury, gold, and bismuth. The reason why we say most of these heavy elements with many core electrons, this term called core electrons, you know, when you talk of interactions, a molecule or a solid, out of the three properties of atom, the electron, the proton, and the neutron, the one that contributed or that participated in interactions is the electron. So, but all these heavy ions now, all these heavy elements now, their core electrons reside in the core of the element, and they don't contribute to the interaction. And that is why most of these heavy elements are regarded as a paramagnet material. So the magnetic susceptibility of various molecular fragments is called Pascal constant. Now, diamagnet material have a relative magnetic permeability that is less than or equals to 1. Therefore, a magnetic susceptibility which is less than 0, this means that diamagnet material are repelled by magnetic field. Take note of that word, that diamagnet material are always repelled by magnetic fields. However, since diamagnetism is such a weak property, its effects are not observable in everyday life. For example, the magnetic susceptibility of diamagnet such as water is approximately negative 9.05 to the power of minus 6. The most strongly diamagnet material is bitumen or bismuth, which is minus 1.66 times 10 to the power minus 4. Although pyrolytic carbon may have a susceptibility of minus 0.4 in one plane. That is, there are 3 planes there. In one plane is minus 4.0. In other plane, it can be higher or lesser than that. Nevertheless, these values are order of magnitude smaller than the magnetism exhibited by paramagnet and ferromagnet. So all conductors exhibit an effective diamagnetism when they experience a changing magnetic field. The Lorentz force on electrons causes them to circulate around, forming eddy current. So eddy currents then produce induced magnetic field which opposes the applied field, resisting the conductor motion. So, you know, in our days in secondary school, when we are discussing motor, this concept of eddy current was introduced to us, but we don't know much about it. So the idea is that when you have an eddy current, there must be an induced magnetic field that will tend to act in the opposite direction to the field. So in that case, trying to resist the conduction, the motion of the conductors. So the magnetic susceptibility per unit volume is defined as this, which is question 2.3, where M is the magnetic moment per unit volume or magnetization, and H is the magnetic field intensity. So diamagnetism explains the tendency of electrical.
Sorry, sir.
Yes, you have a question?
Yes, sir.
Yes, I'm with you.
Can I define magnetic susceptibility by using this formula only?
Sure, you can define by using this formula, but you have to define each of the terms. What is M? What is H?
Okay.
You get it
No
now?
problem. Thank you, sir. Yes,
So
sir.
once you write the equation, then you define it using what is the M, because to a layman, someone that doesn't understand
Yes,
the
sir.
concept of physics, he doesn't know
Thanks.
what M is, he doesn't know what H is. But once you give the definition of each of the term, so the person will know, okay, this is what this stands for. Is that taken?
Yes, sir. Yes, sir.
Okay, good. So diamagnetism explains the tendency of electrical charges to partially shield the interior of a body from applied magnetic field. So for an atom in a magnetic field, the motion of the electron is the same as a possible motion in the absence of magnetic field intensity, except for the superposition of a common precision of angular frequency. So what I'm trying to say here is that there is a way of linking the magnetic field the magnetic field intensity with the angular frequency, and which give us equation 2.4. So the precision of the electron distribution is equivalent to diamagnetic current. So by the time you try to resimplify this expression, bringing in current and all this thing, you have this expression. E here is just the charge, the electrical charge, and H here is magnetic field intensity. Then M is the mass, and I think C is the speed of light. So as the magnetic moment mu of a current loop is given by the product of the current, as the magnetic moment mu of a current loop is given by the product of the current by the area of the loop. So just like trying to substitute this expression here, you have mu over H to equals to this. So where Z for electrons, where P rho square is just x square plus y square, is the average of the square of perpendicular distance of the electron from the field axis. This is just in a 2-dimension, x and y. But if it is a 3-dimension, it will be x square plus y square plus z square. But in this case, you are just considering a 2-dimensional concept, and that's why you have x square plus y square. So in terms of the mean square distance, r square, so you can see what you have here now. This is when they consider them in a 3-dimension concept, x square plus y square plus z square from the nucleus. We have r square to equals to this. For a distribution of a charge, which on the average is spherically symmetrical, so that x square is equal to y square is equal to z square. What I'm trying to say here is that you have equal distance across all the symmetries. So in that case, the system is symmetrical. So the distance from x to y to z are equal. That's why you have your x square, y is equal to x is equal to y is equal to z. Then the magnetic susceptibility per unit volume is if n is the number of atoms per unit volume. So you now have this, which is your z, the charge, the numbers of atoms per unit volume, then the distribution distance over the mass and the speed of light. This gives you a different concept for diamagnetism susceptibility. So equation 2.8 is the Legendre expression that has been used to calculate diamagnetic susceptibility. So take note, somebody can ask you to just write an expression for Legendre equation in terms of susceptibility. This is what they are asking you to do. Just write this expression. Then you define each of the terms. What is Z, what is N, what is C, and what is R. Now, self-assessment exercise now. Explain, can you see now what I just said is what was the first question here. Explain all the symbols in Legendre expression and state their SI unit. So you are asked to explain each of these. What is Z? What is E? What is N? What is M? What is C? And what is R? These are things, if you go through the note very well, we have just this. Z is the electron, E is the electrical charge, N is the numbers of atoms per unit volume, your R is the distribution distance, that is from the distance from the nucleus, and M is the mass, and C is the speed of light. So these are things you are expected to state here and give the meaning of each of them. So the second thing, then explain why the magnetic susceptibility of diamagnetic material will always be less than 0. The answer to this problem is here. If you read this place, diamagnetic material have a relative magnetic permeability that is less than or equals to 1. Therefore, the magnetic susceptibility which is less than 0. So if you can interpret this statement, you answer this problem. This second problem here, explain why the magnetic susceptibility of a diamagnetic material will always be less than 0. That statement clearly explains the reason why the value is always less than 0. Any questions so far? Any question?
No, sir.
Okay, good. So let's move to the next thing, paramagnetism. We have discussed diamagnetism in the previous session. Now we will discuss paramagnetism. Substances with a positive susceptibility are called paramagnetic. You know, substances with negative susceptibility are known as diamagnetism. But those with positive are now known as what? Paramagnetic. So positive susceptibility can be found in 1, all atoms and molecules that has odd numbers of electrons. Please take note of all these 3.2. Example of such atoms and molecules include sodium atoms, nitrogen 2 oxide. So all free atoms and ions with a partly filled inner shell. Transition element, ions, isoelectronics with transition element, rare earth and antinite element. An example is manganese 2 plus, gadolinium 3 plus, and uranium 4 plus. And the last one are metals. So in all these element or compound, we found positive susceptibility. And in the process, most of these compound or elements are known as paramagnetic element or material. So paramagnetic is a form of magnetism whereby paramagnetic material is always attracted when in the presence of an external applied magnetic field. So in contrast with this behavior, their magnetism are repelled. But in the case of paramagnetism, they are attracted. But in the case of their magnetism, they repel when they are inside magnetic field. But for paramagnetism, once they are inside applied field or magnetic field, they attract each other. So paramagnetic have a relative magnetic permeability greater than or equal to 1. That is positive magnetic susceptibility, and hence are attracted to magnetic fields. So the magnetic moment induced by the applied field is linear in the field strength and rather weak. So paramagnetic materials have a small positive susceptibility to magnetic field. These materials are slightly attracted by a magnetic field, and the material does not retain the magnetic properties when the external field is removed. Take note of that statement. This material are slightly attracted by magnetic field, and the material does not retain the magnetic properties when the external field is what? Removed. So paramagnetic properties are due to the presence of some unpaired electrons and from the realignment of the electron path caused by the external magnetic field. So paramagnetic material include magnetism, molybdenum, lithium, and tantalum. So I will give you a very simple example of this that is common to us that we use at house these days. You know, in some houses these days, they have electric bell. So once you press the bell and a
Sir?
current flows through, it induces paramagnetism and it will start producing sound. Please,
Àbúrò woman
please, can you
Tẹ́lifí.
mute your mic?
Come.
Please, can you mute your mic?
Where's that woman from?
Paul, please, can you mute your mic? So the electric bell that we use at our various houses these days has a concept of paramagnetism in it, because once you press the bell, it will induce a field and it will produce a sound. So magnetism takes place. But immediately you took off your hand from the bell, it loses the magnetic properties and it doesn't produce any sound again. So that's why we say that this material are slightly attracted by magnetic field and the material does not retain the magnetic properties when the external field is removed. Once you take your hand off it, you have break the magnetic interaction and it loses the magnetic properties. So now, in the case of ferromagnet, paramagnet do not retain any magnetization in the absence of an external applied magnetic field because thermal motion randomizes the spin orientation. Some paramagnetic material retain spin disorder at absolute zero, meaning they are paramagnetic in the ground state. Meaning they are paramagnetic in the ground state. Hey, Soto, please mute your mic. So because of the external randomization of the spin orientation, some paramagnetic material retain spin disorder at absolute zero, meaning they are paramagnetic in the ground state. Thus, the total magnetization drops to zero. When the applied field is removed, even in the presence of the field, there is only a small induced magnetization because only a small fraction of the spin will be oriented by the fold. This fraction is proportional to the field strength, and this explains the linear dependency. The attraction experienced by ferromagnetic material is non-linear and much stronger, so that it is easily observed For instance, by the attraction between a refrigerator magnet and the ion of the refrigerator itself, consider a paramagnetic material containing n atoms per unit volume, each having a magnetic moment mu. If a magnetic field H is applied to the material, magnetization occurs from the orientation of the magnetic moment, and the thermal disorder resists the tendency of the applied field to orientate the moment. The energy of interaction with the applied magnetic field is V is equals to minus mu dot H. Mu here is the magnetic moment, and H here is the magnetic field. So if you take it to thermal state, for thermal equilibrium, magnetization can be derived as M is equal to N mu L A. A here is the lattice constant. So where A is the mu H over KT and the Lagrange function Na is this. This is a trig function, and at the end of the day is A over 3, which I said is the lattice constant, and magnetization is equal to this. So in the limit mu over H divided by KT, this is thermal state now, far less than 1, the magnetization susceptibility is this. So where C is this is known as Curie constant. So the 1 over T temperature dependence is known as the Curie law. So equation 12.2 is known as Lagrange equation. Now, the self-assessment exercises are differentiate between diamagnetism and paramagnetism. I've discussed this extensively and I've explained, even give some example. So they said list 5 materials that are diamagnetic and paramagnetic. We have many of them listed here. You can see them, this magnesium 2 plus, gadolinium 3 plus, uranium 4 plus, nitrogen 2 oxide. So if you go through them, you can be able to extract those information and answer the self-assessment questions here. Now, any question? Any question? Okay, if there is no questions, let's quickly go over the last concept here, which is ferromagnetism. In the case of, the last 2 concepts that we have discussed mainly rely on the field. When you bring the field to them, they attract, they produce. When you take away the field, they lose the magnetic properties. In the case of this one, it has its own magnetic properties, but all the spins in this case tends into one direction. So now we explain the ferromagnetism and antiferromagnetism. Ferromagnetism is the basic mechanism by which certain materials such as iron form permanent magnet or are attracted to magnet. In physics, several different types of magnetism are distinguished. 1. Ferromagnetism, including ferrimagnetism, is the strongest type. It is the only type that creates forces strong enough to be felt and is responsible for the common phenomenon of magnetism encountered in everyday life. Other substances respond weakly to magnetic field with 2 other types of magnetism, paramagnetism and diamagnetism, but the forces are so weak that they can only be detected by sensitive instruments in a laboratory. An everyday example of ferromagnetism is a refrigerator magnet used to hold notes on a refrigerator door. These days now, we use whiteboard marker in the classroom for teaching. And you will see that if you want to clean the board, we use a duster. And if you put the duster on the surface of the board, it will be attracted to it. What makes it to attract to the surface is because there is presence of ferromagnetic materials in the duster. And that is why you can put it on the board and it will be attracted to it. Even at home, the door of the refrigerator, if you put a small iron on it, it will be attracted to it. It's because that surface has the presence of a ferromagnetic properties in it, and that is why it can be attracted to it. So they are known as permanent magnets. So material that can be magnetized by an external magnetic field and remain magnetized after the external field is removed are either ferromagnetic or ferrimagnetic. As an other material that are noticeably attracted to them, only a few substances are ferromagnet. The common ones are iron. So take note of this now. Somebody can ask you to differentiate between ferromagnet and diamagnet with examples. So you should know that ferromagnetic materials, an example is iron, nickel, and cobalt. and most of their alloy, some compound of rare earth element, and a few naturally occurring materials such as lodestone. So ferromagnetism is very important in industry and modern technology, and is the basis for many electrical and electrochemical devices such as electromagnet, electric motor, generator, transformer, and magnetic storage such as tape recorders and hard disks. So the next thing we are going to be discussing is Curie-Weins law in relation to ferromagnetic. So ferromagnetic materials are substances that possesses a magnetic moment even in the absence of an applied magnetic field. So the saturation magnetization ms is defined as the spontaneous magnetic moment per unit volume, and the Curie point Tc, that is Curie temperature, is the temperature above which the magnetic moment vanishes. So if the ionic and atomic magnetic moment of a paramagnetic substance can be made to line up the same way by the addition of an interaction, then a ferromagnetic substance will be formed. This interaction is called Weins field and the molecular field or the exchange field. Weins was the first to imagine such a field. The motion of thermal agitation of the elementary particles opposite the orientation effect of the Weins field. So Perry-Weins assumed that Weins field BE is proportional to the magnetization. So this is what we wanted to derive before we start giving that stories. So Weins field BE is equal to lambda m. M is magnetization. So lambda is the Weins field constant, independent of temperature. This is not dependent of temperature, but you can remember, you recall that susceptibility is temperature dependent. So somebody can ask you to give in a sentence the difference between the Weins field constant and susceptibility. So susceptibility depends on temperature, but the Weins field constant is independent of what? Temperature. Take note of all these things. So the susceptibility above the Curie point can be deduced from the Curie law using this formula. So note that we have taken the magnetic field as the sum of the applied field and the Weins field, and this gives us this expression. So the rest is just to try to do substitution. Then doing that, you can be able to derive equation 2.16, 2.17, 2.18, and all other equations, just substituting, doing algebra and expanding and all these things. That gives you all these things. Then we have spontaneous magnetization. In this section, we will see how we can determine the spontaneous magnetization of a ferromagnetic substance. A ferromagnetic substance is said to have a spontaneous magnetic moment if it is opposes a magnetic moment. I think we need to stop here because we'll be locked out of Zoom now. We have just 40 minutes. So if you have any question, you can ask before I stop this, before they lock out, so that I can save the video and send to you. Any question?